So we want to find a series solution to this differential equation. Of course, you already know a couple other techniques that you can use to solve this differential equation. So that's what I thought to choose a question that you already know how to solve it in some other method, so you can verify your solution based on those. So we have y double prime minus xy equal to 0, and we want to find a solution around x0 equal to 0. So it's like we can make the assumption, when we talk about series solution, we make the assumption that our solution is going to look like a Maclaurin series, since we are looking at x0 be 0. So if that's our solution, because we're looking at the differential equation, we need to find the y prime, which we take the first derivative of that function, we get the y prime, and we get the y double prime. So if that's the solution, if that Maclaurin series is a solution, we can plug it into an equation and see if we can find the coefficients. When we talk about finding a series solution, basically we know the x variable. Those are the variables involved in the equation, but we need to find the coefficients, what are the a's of n. So this whole process is to find those coefficients in order to define our series solution to the differential equation. So what we do, if that's our solution, we're going to plug it into our differential equation. So the y double prime goes instead of y double prime, which we have it here. The y is going to go to, instead of the y, which is, we have it here, equal to 0. So we have two series. In order to add series, the indexes should match and the power of x should match also. So in order to do that, the first thing we need to do is we need to see if we can change that index to 0 to infinity. So if we substitute n by n plus 1, n plus 2, n is the dummy variable, so you can replace n by any other variable. So I'm going to replace n by n plus 2. So wherever we have n here, I'm just going to put n plus 2. So what will happen with the index is going to be n plus 2 equal to 2, which is n equal to 0. To infinity, instead of that n, we're going to have n plus 2. Instead of that n minus 1, it's going to be n plus 2 minus 1, which is n plus 2. A sub n plus 2 times x to the power of n, because n plus 2 minus 2 is n. This one, we have that x outside, so we want to bring everything inside so we can match up the variables. So we distribute that into that series. We get a sub n x to the power of n plus 1. So now we have two indexes, but then we notice that the power of x are not compatible. So what we're going to do, we're going to substitute n by n minus 1 in this question. So n minus 1 plus 1, that gives us n. And as we work it out, we're going to substitute n by n minus 1, so that goes from 1 to infinity, and we'll leave that one as it is. We're not going to touch it. So now we have two series that they have the same index and the power of x are the same. So that means we can combine the two. But then we notice the index in this one goes from 1 to infinity, but the index of this one goes from 0 to infinity. So in order to match the indexes, we're going to pull out the first term. We're going to pull out the 0 term from this series. So we plug in 0, we get 2 times 1 times a sub 2, x to the power of 0, which is 1, so we get 2a2. And then what we have left from the series, we have 1 to infinity, n plus 2 times n plus 1, a sub n plus 2, x to the power of n, and we leave the second one as it is. Now we have same indexes, same power, so it's like adding polynomials. We can add up the coefficients. So we have 2a2 on the outside. Inside we're going to add up the first coefficients, 2 plus 2 times 2 plus 1, a sub n plus 2 minus a sub n minus 1. So in order for this polynomial to be equal to 0, we need the coefficients be equal to 0. So we move here. So the 0 term was 2a of 2. So a of 2 we know is equal to 0. So for n equal to 1, 2, 3, 4, 5 as we go on, we have this recurrence relationship. So this is a relationship that explains how the different terms are defined. So we plug in 1. We plug in n equal to 1, we get a sub 3. 1 minus 1 is 0, so a sub 0 divided by 3 times 2. We move on to the next term. So we want to do this a few terms, and you'll start noticing that a0 start repeating, a1 start repeating, and if there is any a2, you will see a2 repeating also. So we plug in n equal to 2, we get 2 plus 2, 4, a sub 1 over 4 times 2, because 2 plus 2 is 4 times 3. We plug in n equal to 3, we get a sub 5, we have a2 over 5 times 4. So nothing is repeating so far. We move on to the next one. So we plug in the next number, n equal to 4. So we have a of 6. So 4 minus 1 is 3. You have 6 times 5. So now you see that a3 is repeating. So if we were to find a5, we could just put that a0, that formula into here, and we would have a0 divided by 6 times 5 times 3 times 2. The same with a4. So once we have a7, we can write it in terms of a4, we can write that in terms of a1. So very much all those terms that we have 4, 7, 10, as we go through, we can write all of them in terms of a1. And all the coefficient on this side is 3, 6, 9, 12, as we go on, we can write it in terms of the a0. a2 was 0, so once we plug in for a sub 5, that's 0. That a sub 5 goes to a sub 8 is 0. So all those terms are also 0. So if you had like 5, we would have 11, 14 as we go on, those terms would be 0. So if you put these terms together, we notice that as we go through, they are very much the coefficient of 3. So we have 3k, we have 3 times 1, 3 times 2, as we go on. So a of 3k is very much a0 times 2 times 3 times 5, all the way to 3k minus 1 times 3k. So that's like that 3k, and that's 3k minus 1. For this series, the pattern we notice, we have 3k plus 1. So we have 3 plus 1, 3 plus, so we would have 6 plus 1 as we go through that. So that basically we're going to have 3k plus 1. Everything is in terms of a1. So we have 3 times 4 all the way to 3k times 3k plus 1. Because if that's 7 is 3k plus 1, that's the 3k plus 1, that's the 3k. That one, they're all 0. So if we put this together, our general solution, remember, we do all these different terms because we want to define that series solution. What are the coefficients? So if you put all the coefficients together, we notice we have some of them in terms of a0. So we have a0 times 1 plus that series 1 to infinity, x to the power of 3n, because we have 3k. So, and very much the same coefficients. And we have a sub 1 multiply, we had 1x out, so we have x plus going from 1 to infinity of x to the power of 3. So remember that's n1, that's why we have x to the power of 1. And we have that coefficient as well. So that is the general solution of that differential equation. And as you will see, the a0 and a1 are like c1 and c2 are the two coefficients for the solution.